Okay, so I start with a brief introduction of our distinguished speaker today. So first, welcome everyone to this RISC Colloquium, whether you are in person or online. So my name is Trinity. I'm an assistant professor from the Department of Math and Stats. And it's my pleasure to introduce Dr. Bing Zhou from the University of Connecticut. So Dr. Zhou graduated from the University of Alberta with a PhD in mathematical finance in 2013, and he joined University of Connecticut in 2017 as an assistant professor, and he was recently promoted to associate professor. Okay, and Dr. Zhou's research actually encompasses a wide range of fields such as mathematical finance, actuarial science, and stochastic optimization. And he has published actually more than 30 papers in top journals in those fields. And so he's going to present to us one of his recent works, Linear Classifier Models for Binary Classification. So let's take it.
Thank you. Thanks for coming to the talk today, and I really appreciate your presence. It is actually my first time physically at York University. Although somehow the story starts long time ago. Yang worked with me for many years. He was at York when I first met him, but that was at a conference at the University of Toronto. And if he didn't leave, I probably would have come earlier. And then, shortly he left, and also, now I'm working with the young people here as well. So, but today I'm going to present something that is a little, let's say, unusual for me, because my main interest is in stochastic control and its applications in actuarial and financial mathematics. But today I'm going to present something that is more traditional in actuarial science, that's predictive analytics. Okay, and this talk is based on a joint work with Hin Chong. He's right now assistant professor at Simon Fraser University. He graduated from UConn a few years ago. His supervisor was Emil Wilders. Probably many of you know him. This is sponsored by CAS by its individual grant. So before I go into any details, I try to explain to you the title. Okay? If we go back, the title says Linear Classifier Models for Binary Classification. That means the problem we are trying to study is a binary classification, right? Or using the fancy language, that would be a specific supervised learning problem. Right? In this problem, you observe both x and y. So y is something you are trying to predict, because this is a binary problem. So y will take only two values, 0 and 1, or two categories. Right? So the values, they don't matter. It's just there are two categories. So that is the general problem we are trying to study. Okay. Another keyword in the title is linear classifier. Right. That means the score function is a simple one. Right? It's linear. Right? We do love linear functions in actual science. Right? You see them everywhere. So given a value of x, so given a vector of features, you get a score. That's a linear classifier. And how do you predict? Right? The rule is pretty simple. If the score function is positive, you predict 1. Otherwise, you predict 0. Right? So of course, 0 can be any number. You can change it, but for that you can really observe it. Into the alpha. Right? So it doesn't matter. So 0 is pretty much without loss of generality. So under this relatively simple framework, the true problem is going to be estimating alpha and beta, right? Because the rule is simple, right? Everything is intuitive. The only question boils down to estimating alpha and beta, and that distinguish, different approaches. The common one, not just in actuarial science, in general, right, in statistics, is to, you minimize MSE because this is supervised, right? You have a target. So you can minimize the MSE, that's a mean squared error, one of the most popular loss function. Or you can do maximum likelihood, right? So that is the method for the so-called logistic regression. That is the benchmark for doing classification. But what could go wrong, right? We are presenting this, which means we don't follow those standard ones, right? Otherwise, there's no point of writing a paper. What could go wrong? The standard loss function is fixed, meaning what that means is, well, for all of us, if we are given the same data, we are going to arrive at the same alpha data. Right? That's the meaning of fixed loss function, because we solve exactly the same problem, even though you and I may differ a lot on what should be the best choice. But as long as we follow the standard approach, let's say you are trying to maximize the likelihood, all of us are going to arrive at the same solution, right? That means the trade-off is not really controlled, right? Because we are different, meaning we have different perspectives on false positive and false negative. Right? The next slide will show you exactly what they are, but intuitively in statistics, there's type 1, type 2 error, right? Because we are doing predicting, and this is simple binary, right? It can be the true is 1, but we predict 0, or true is 0, but we predict 1, right? So there are two types of errors, right? And we have different perspectives on which one is more important, right? However, if we follow the standard approach, that cannot be, let's say, customized to reflect your own perspective on it, right? So because it's fixed, so what would be a possible solution, right? There are many solutions. Here, what we consider is a metric loss function. So it is not fixed. It won't be a family. So the loss function will come from certain family, and we argue that that family is reasonable. Okay? Because there is a parameter, or there are more than one parameters. But if we differ on something, we will pick different parameters. And because the loss functions are going to be different under different parameters, right? We're going to get different alpha and beta. So that will reflect our subjective opinions on what we care more or what we care less. Okay. So that is the summary of what I'm trying to do. So now let's take a look at the trade-off. So that is what people call confusion matrix, right? So along the diagonal line is the correct prediction, true, right? So both would be the correct one. Off diagonal is where you make errors, right? So here is false negative, right? The actual one is positive, but you predict negative, right? Likewise, negative. And the other one is false positive. So those are the two types of errors you might make. Right? So here's a quick example to give you a better idea. Right? So I mentioned there are two categories, 0 and 1. Right? So throughout the talk, you can see 0 as standard, 1 as substandard, because we are doing insurance, right? So standard means it's a good policy or good applicant, which means you should accept, right? So 1 means it's a substandard risk you should reject, okay? But of course here, accept and reject are weak sense, meaning, well, if you see a substandard risk, well, you can either reject or you can ask for a higher premium, right? And then you let the applicant to decide, okay? So now we can easily identify the false positive and the false negative, because then we have, so 0 is negative, right? 1 would be positive. Then we can have more precise meaning of what is negative, what is positive, false positive, what is false negative, right? And now I give you, well, here's a quick examples on why it's important to have the ability to adjust, right? Which one matters more when you are doing this problem, right? So here's, from the insurance point of view. Actually, I think we can think, I can give you a more realistic example. Has nothing to do with insurance, okay? But before the pandemic, we had a good-sized master program on financial math. Like every semester, we get 100, 120 applications, and we usually took 30 around that number. So it is highly selective, meaning I can set. So what I do back then is when I see an application, I will only accept those I consider to be top. Those, not doesn't need to be weak. Somehow okay, I will reject because I have enough good candidates. Now things have changed a lot. Probably some of you know as well. Now, as long as they are not too weak, I accept. So you see, my objective is changing, right? And then that affects how I make decisions, right? That is exactly here, right? If you are a new company, if you want to enter a new market, you have to set relatively high false negative because you are okay accepting a positive, but you think it's a negative, right? Because it's okay to accept someone along the boundary line. But if you are already a mature insurer, well, your priority will be those good ones, right? Making a few errors on them is fine, but you don't want to take a potential substandard. So, depending on your business objectives, you do have different, let's say, objectives, right? That is very natural, and we are trying to handle that. And this gives you another standard one. We are going to compare to the standard approach. For the binary regression, that's going to be the logistic regression. We all started this, from the textbook, right? So this is the loss function. What it means is it has two components. I will get to that later on when I introduce our loss function. This will be a special case, but roughly speaking, you can see that because we are trying to maximize, right? So when this one is 1, you are trying to get this to be big. And when this is 0, you try to get this to be big, right? That's the perspective, right? And for the logistic, your link function takes that specific form, okay? And there's another choice called the probit function, which takes the link function to be the CDF of a standard normal, but they are very close. But the basic thing is, doesn't matter which link function you choose, same data, same estimate. So that is the message I'm trying to deliver before we propose our model, right? They cannot really adjust the impact, how false negative and false positive affect your decision. Right? I give you a simple, realistic example that even for the same person, my perspective could change, and that affects my decision making. Brief literature. I mean, I'm not an expert on this field, so there's a huge possibility that I have missed a lot. But this slide is basically to show you that binary classification is very, very popular. It's prevalent in financial and actuarial world. Right? When you submit application for insurance, right? It's naturally a binary question. Should I accept or reject, right? If I'm representing the insurance company, right? There are so many things that fall under this category. So now let's go to the second section. I will pretty much give you all the details of our model, okay? So it's a binary. So X will be, there are many names for X, right? You can call it independent, you can call it covariates, features, whatever you want to call it. Right? So X stores the information for prediction. And Y will be the target, what you are trying to predict, right? There are two classes, 0 and 1. Again, 0 will be the standard risk. Actually, it will be the majority class. And 1 is the substandard risk. It will be the minority risk. I don't really handle minority majority in this paper. The reason I put that is because for non-life insurance, okay, the majority is always 0. Let's say auto insurance, right? 95% of policies will be clean. They do not report any claim. That's 0. Right? So 1 will be the policies that file a claim or more than a claim. Right? So that's why we have the majority minority. That's a totally different issue. That's the so-called imbalance. Right? When you have such an imbalanced data set, how do you do prediction? Right? That is a very tough problem. But we don't deal with it here. The discrimination function is really, really a bad name, right? Because nowadays you shouldn't use that word. But let's call it a score function. So it's a linear score function. So what it does is to map your X into a value. Right? So X will be usually will be in high dimension. especially for insurance companies. Nowadays, they collect too much data. So X will be in high dimension, and this D will map an X value to a real value. Okay, and then the rule is if this is positive, you predict 1, negative, predict 0. So that's the basic prediction rule. So how do we estimate alpha and beta? So we consider this type of loss function, which comes from this very nice biometrical paper. It's one of the top journals in statistics. So what they propose is very general, right? Because here, U0 and U1, you just need them to be increased. Nothing else, right? Because they are penalties. So let me explain, right? So let's explain the first one. Here is a loss function, so you are trying to minimize, okay? So this will only be non-zero when y is 0, right? Because y is either 0 or 1. So when y is 0, that means it's a negative case, right? But if this is big, you should predict it as positive, right? That's the prediction. So that's when you penalize. The true y is 0, but somehow your score function is big. Then you should penalize, right? Because a big score function, meaning you're going to predict the case as positive, but in fact, it's a negative one. So when you have y being 0, but your score function is large, you should penalize. So that's the first term. Likewise, the same thing for the second term, right? If y is 0, there is no error. So y has to be 1 for the second one to contribute, right? Then y is 1 means it's a positive case, but then you predict to be negative when you have small loss function. So that's why we put a negative to penalize. So what we say is, in this loss function, there are 2 terms. The first one accounts for the penalization of false positive. And the second one accounts for the impact of false negative. And then how you choose your U0, U1 will determine how you want to penalize either one of them. Okay, so of course we penalize both, but the weight on which one is more important depends on U0 and U1. Okay, so that's too general, right? It's probably not too useful for a particular use. So there are many people. First, there are many people working on the theoretical side. Whether this has a minimizer, right? So that's the first theoretical question, right? Luckily, we don't need to deal with this. There's a nice paper by Owen published in Journal of Machine Learning Research. You see, Journal of Machine Learning, it started actually very, very early on. Only recently it hit off, right? Nowadays, JMLR is considered as an alien journal, as a very, very high impact factor. That's because machine learning, it's a hot topic, but the journal exists for a much longer time. So a few remarks. There are actually many benefits of such a LCM, linear classifier models. So first of all, they are linear, so they are easy to interpret, right? Nowadays with machine learning, sometimes what you predict, you don't tell that much, right? It's just a black box. You input, you output. Right? There's nothing you can tell in between. But this is not. This is somehow traditional, right? So it has a great interpretability. That's great, right? Because if you use this in pricing, you do need that, right? You need to tell how each factor affects pricing, right? Otherwise, especially nowadays, fairness is such an important topic. Right? You don't want to get into legal issues when using certain factors you are not supposed to use, right? So here it's very flexible because U0, U1 later on I will show you that there are so many ways to get a nice candidate for them. In fact, the simple linear score function is actually optimal in many sense. Okay, but that's a technical issue. So let's move on. Let me give you a technical result, which we do use. Okay, so thanks to this paper, under the consistent condition. So what consistent means is this model should cover the logistic model. Okay, we already know everything from the logistic model. If the estimate is consistent with that one, when you take certain loss functions, then it should be given in this particular form. So it shouldn't be any increasing function. So if you want to be consistent with the logistic model, the U0, U1 should be in this representation. Okay, constant doesn't matter, right? Because we are doing optimization. Then the only thing matters is W. So you don't need to choose two penalty functions. You just need to choose one, which we call weighting function. So this W has to be positive. Okay, and that's it. Right. Here is the result we didn't explore. Okay? I mentioned that for most non-life insurance data, it is highly imbalanced. Right? Most people develop new tools to handle it. Actually, one of Emil's last PhD students, Bunky, did her work on handling imbalanced data. Okay, and this is a asymptotic result. We didn't explore, but it has the potential. So some examples of our W function. The first one is something we will use a lot. We call it exponential weighting function. Well, that's because we take exponential as W, right? You can do a simple calculus to get U0, U1, right? So here, lambda is going to be your tuning parameter. It's between 0 and 1, and it controls how much you want to penalize on each side. Actually, this one, not this general form, the half case, the case of lambda equals half is the famous ADA boost. Actually, Emil and his student modified ADA boost to handle imbalance because ADA boost is not good on handling imbalanced data. And their work is to propose new, let's say, adjustment to the traditional ADA boost to handle. Okay, so this obviously includes ADA boost as a special case. This is what we call the log weighting function. I mean, we don't really know what to call because they don't have actual names. I think we thought of this from ourselves, maybe. There are many cases. It's a lot more complicated than the explanation. I only showed you U0. Okay? U1 is something similar. It's just more complicated. Again, here is parametric, right? Gamma is going to be the tuning parameter. It's also between 0 and 1. The last one is the famous logistic. So if you choose your weighting function to be this particular form, your U0, U1 will be in this. And that will give you exactly the logistic function. So let's go back a few. Where's my logistic? It's here, right? Pi is in that form, right? So if you do a little manipulation, you will see that they are exactly the same. They differ only by a negative sign because here is a loss function. So you are trying to minimize. What they do is likelihood. So they are trying to maximize. So the standard logistic is nothing but a very special case under this model, right? Because any possible W, right? There are some conditions, but they are very weak. The choice is infinite, right? So we only considered here I put 3. It's really infinite. The reason we put those 3 is because I can do calculus to show you what U0, U1 is. And having a specific U0, U1 will allow me to solve the optimization problem easier. But now with so many powerful algorithms, you don't need a specific U0, U1, right? We calculate this by hand. You don't need to do it anymore, right? You can pick any sophisticated positive function W, and then you will get something more complicated. Okay, I just want to show you something simple. Why this family will work? Right, so I give you some quick results on the loss function. Okay, this purple line, almost linear, is the logistic line. So that is how logistic model penalizes the on the specific scores. Right, you see that if you have a very big D, right, you are supposed to determine that quickly, meaning you should penalize heavily, because for such a big score function, you shouldn't hesitate, right? But logistic is hesitating, right? It's linear. The weight grows linear, right? But we have something that grows much faster, right? Which means those will be more powerful than the logistic model when it comes to penalizing this part, right? Because if you have a score function of 6, you should easily predict it as 1. You shouldn't hesitate. But if your loss function grows slowly, the penalty is not strong enough, right? How do you quickly determine it? Is when you put enough penalty, right? Then you know I shouldn't hesitate, right? I should immediately say this should be a positive case. And the same reason here, right? For -6, you should know what you should predict, right? It should be a good policy, right? You shouldn't hesitate, right? So that's the thing. But of course, you can, if you look at those exponential colors, here is the, what is it? The green, this line, they penalize good on positive, right? But for negative, it doesn't behave well. So that is the reason why you cannot minimize type 1, type 2 at the same time, right? You have to choose one. Those working well on one side will be the worst one on the other side. So that's exactly the type 1, type 2, right? If you squeeze one side, the other side is not going to pop up. So that's why it's important that you know which side you are trying to penalize more, okay? But in either case, logistic is growing slowly, right? So it's a decent model, but it's not going to give you the best performance if you really know what you are trying to do. Okay, calibration. This is relatively easy to calibrate. That's because for the example we consider, we can actually do it analytically. We can show that, okay, we can calculate the first order condition, and then we can show that the second order condition, well, the Hansen matrix is strictly greater than the other. So it's necessary and sufficient. By the way, that's the reason why we pick those special examples. That's because we want our wildcard candidate to be the true minimizer, right? But of course, nowadays, for many optimization algorithms, they don't really guarantee it is the global solution, right? That is always an issue, right? What you get, is it a local or global, right? Here, it has no problem at all, right? Sometimes we only care about the final result, right? We don't care that much whether that is the global minimizer or not, but here it is. So that's why we consider something more tractable. Now, with that in mind, I move on to discuss. So first, the study will be simulation. So it will be very, very simple. There are 2 classes. 0 has 10,000 policies. 1 has 500. Okay. Our covariates only have 2. The first one is age. So the applicant's age. 2 is the vehicle's capacity. So that will be some scaled value of the engine size. So your intuition should be, for age, the younger the age, well, the better the chance it will go to N1, right? Because that's the intuition, right? So if you are young, if you are getting your policy, you are considered as substandard, right? So once you get old enough, you're considered to be a good applicant. Likewise, so if you have a big engine, that's more likely to put you as the substandard risk. So we apply very simple, the normal distribution. Right? You have 2 classes. For 0, we put a specific value, but for 1, you can think of it as a mixture. Right? The reason we are doing the mixture is that we want the problem to be more challenging, right? So if you have 2 specific clusters, then it's very, very easy to do the classification, right? So that's why we manually add the difficulty. That the graph says all. So the reason why we put this to be a mixture, that is because we don't want the problem to be trivial. So we want some red points to be mixed with the blue ones. So some substandard and some standard are quite mixed together so that you don't easily separate them. Okay, so that's pretty much the reality. Right? You will not have 2 quite distinctive clusters. Right? Then it's easy to do the classification. Right? The problem becomes more interesting when some of the points are in the domain of another cluster. Right? So once we apply the model for, actually we did for all examples, right? Here we have example 1, example 2, and example 3. Example 3 is the logistic. So logistic is our benchmark. So here I think I'm only showing you example 1. Example 2 is similar. So how do we interpret? So first of all, let's look at the left-hand side. Your x-axis is the true positive. Your y is the false positive. So for any given x, you want the curve to be lower, right? So the lower the better, because y is the error, right? Is the false positive. So what you understand is you pick your target true positive, right? That's when you draw a vertical line. Okay, then the lower the better. Well, the example 1, that is exponential weighting family, right, is much better than the logistic, right? Logistic is way up, right? The logistic model is close to the exponential when lambda is 0.1. Okay, but as long as you choose relatively big lambda, actually as long as lambda is almost greater than 0.2, you can outperform the logistic in almost all the good regions, right? I mean, they were somehow close at some point, but somehow, you know, if you want, let's say, after 92%, right, the exponential with lambda greater than 0.2 will outperform the logistic model. Okay, that's where you have a very high target for true positive. Okay, likewise for true negative, something similar. Okay, except in this case, logistic actually is doing very well, because logistic is somewhere here, right? And in that case, so in this region, in order to outperform logistic, you need a very small lambda. You need your lambda to be less than 0.1 in order to do better than the logistic. Okay, I will tell you why logistic is doing so well here. Okay, but anyway, the impression is simple. Right? By choosing a specific lambda, you can do better than the benchmark. Right? So that is quite intuitive, especially for this one. Right? Okay, so now why for our simulation study, logistic is doing so well for the high value of true negative? That is because 0 is negative, 1 is positive. For our model, it is, you know, true negative is 90, how much? You can do the calculation, right? Very high, right? That is because the data set itself has very high true negative rate, right? It's 10,000 divided by 10,500 is the actual true negative rate, right? The logistic model is doing well because that's the actual case, right? However, if for such a data set, you want your true positive to be high, then logistic is performing very terrible, right? Because, well, in this case, it won't be a good choice. Okay, and to back up this, we even did another experiment to flip the two sides, to set the positive to be the majority, and then we observe the logistic to perform well on the left, because now the true positive is indeed high, right? So basically, your logistic model will do well if what you want to do is actual case. Okay, but that can, you don't know the truth, right? You don't know the truth, and you can't just say that's what you want, right? Even though you may have such imbalanced case, but you may still want to have high true positive rate, simply because that is your business purpose, right? This example should give you a flavor that the exponential value is definitely more flexible, right? That's for sure, right? Because it's your choice to choose lambda. And when you pick different lambda, you get different results. And another thing you can see is for the same true positive, you can tune your model to do better than the benchmark, right? That's another thing you can achieve when you have more freedom, right? Under this kind of family, right? For logistics, there's nothing you can choose, right? Given a target is fixed, right? If you draw a vertical line, you get a unique intersection. But for the exponential, you have infinitely many, right? Depending on which one fits you the best, right? But of course, it's not always the lower the better, right? It's not you just pick the one, because once you pick lambda to be very close to one, you're the other side. You will suffer from the other side. So you need to balance, right? So that's the beauty of this part of research is it's really up to you to balance, right? For the logistic model, you don't have that choice, right? The model decides for you. You cannot adjust, right? For the logistic model, it is the curve. Now you have many choices, right? Depending on what your goal is. Here there are some specific terms. They are awkward, so that's why I don't say too much of what is high sensitivity, what is high specificity. Right? Actually, maybe better to use the actual meaning. Right? So one of them is high to positive rate. The other one is high to negative rate. Right? So then, of course, if the positive rate is high, then the negative rate will be low. Right? So it's always the one side and the other. Another thing I should mention is that when you consider a classification problem, what I'm presenting in those two graphs are only a snapshot. The reason is because probabilities between 0 and 1, right? I'm only showing you 90% to 1, 90% to 1, right? So this is only one tip of the story, right? It's not the whole story, right? But sometimes this may be your target. So what people do is, okay, so this tiny part is what I showed you in the previous two pictures, okay? If you want to look at the overall that's between 0 and 1, you can plot the so-called ROC, okay, curve. For this, well, something different is the x-axis is false positive rate, okay? Before is the true positive or true negative. So for this, the higher the better, right? Because your x-axis is the false positive and your y is the true positive. So given any false positive, you want your true positive to be as high as possible, okay? So that is the standard ROC curve. What you can say is, of course, you shouldn't expect one curve to completely dominate the other, right? Like I said, it's almost impossible to have a model that will dominate the other on both type 1 and type 2 error, right? If you minimize type 1, type 2 is going to go up likewise, right? So if one model has smaller type 2, its type 1 will be higher. So that's why usually they will cross, okay? For the from 0.9 to 1, you can see that the red one is mostly on top of the purple one, right? Red one is the exponential with lambda equals 0.9. So the overall impression is that exponential with lambda being 0.9 is better than the logistic, okay? But of course, well, you may argue that, you see, for this part, logistic is doing better, right? So that's why if ROC, you have some disagreement on, people can disagree on which one is better because one will be on top of the other over a certain region, but not always the entire region, right? So how do we compare? So that's why people propose another measure that's called AUC. So that is the area under the ROC, right? Because for ROC is the higher the better. The very best is this horizontal, right? So if you have a horizontal line at 1, that is the perfect model, which means doesn't matter what your false positive is, you can always predict the correct one, right? So that is the best. And for the best model, your area is 1, right? Because x is from 0 to 1, y is from 0 to 1. So for the best model, your AUC is 1, is the area under the curve, right? And I also mentioned for ROC, is the higher the better. The higher means the area enclosed by the ROC is bigger, right? So with that in mind, we know that for model comparison, the larger the AUC value, the better the model. Okay, so now logistic is about 97, right? For exponential, it depends on the lambda value, right? But you see, all those are better. The blue are better, red are worse. So we did some experiment, right? So about 0.2 is the threshold. So if lambda is less than 0.2, its AUC will be smaller than the logistic model. For lambda bigger than 0.2, it will be better than the logistic model. Okay. This is the question that one referee asked, because like you see here, lambda is so important, right? Initially we didn't mention too much of lambda. That is because our argument is simple, right? We want the user to choose lambda. How lambda will affect the model is pretty obvious, right? I showed you the two graphs, right? Which lambda should you choose close to 1 or should you choose close to 0? That is quite obvious, right? And our argument is, well, if you are the one who's making the decision, you should know which side you favor. And if you know which side you favor, you know what kind of lambda you should choose. But nevertheless, let me show you a mathematical approach, okay? So what you can do for this is in machine learning or in statistical learning, you call this k-fold validation or cross validation. So what you do is you separate your data into k-folds, okay? And you use some of them. Here we use k-1 fold to do the estimation. We use the remaining fold to do the validation. Okay, of course you need to rotate, randomly select, and then do an average. Okay, so here's the average. So for the validation part, okay, you calculate the average of the value function. I will mention briefly what you may choose for the value function. Okay, so once you choose that, this is an optimization problem, right? You can optimize to find the best lambda. Lambda matters so much, right? And here it comes to another question, because here under this approach, the key is what kind of value function you choose, right? Because everything else is simple, right? Once you choose this, using k-1 fold data to estimate alpha and beta is very simple for our model, because we know first order condition does everything, right? And then calculating this is also simple. So it boils down to what kind of value function you choose. So here I give one example. So of course it's not unique, right? So this is a possible value function in the sense that given the true case is 1, you should predict 1, right? You want this to be big, right? Because that is the correct prediction, right? And we put one more condition, that is your true negative is high. Okay, you see what we are trying to do? 1 is positive, right? So given my true negative is relatively good, right? It's better than 90%. Given my true negative is good enough, I'm trying to maximize my true positive, right? Because this is the true positive. Y is 1 is a positive case, and I want my prediction to be 1. So that is the standard one in statistics, right? Fixing your, let's say, fixing your type 2, okay? Your error, you have a target, you try to minimize the type 1. This is what we are trying to do, right? Of course, this is not unique. You can have different perspectives on your value function. This is a plot of our average, right? Once you have that, you do an average of your value function. And I mean, it's first of all, it's not exactly decreasing, right? You see, the red point is the highest point, so it's about 0.04 in this case. Okay, 0 is a very low value. It is actually in this case, this part. I mentioned, you need lambda to be less than 0.1 to beat the logistic, right? Like I said, one of the conditions is true negative should be greater than 90%. So that is why you are under this graph. Okay, we know lambda should be small, should be smaller than 0.1. And what lambda you should choose according to this type of value function, your lambda should be 0.04. Okay. But again, this is only an illustration. As long as you choose your value function, this is very simple to do, at least the numerical. Right? We didn't solve this analytically. We plot and you can see the solution. So now let's move on to do the empirical research. Okay, we use the data from there's a title from the LGPIF dataset, and probably that is one of the most well-known data sets in actuarial science, right? Everybody is using that just because it's free, and it is a good representation of non-life or property casualty insurance side. Here we consider the BC, so the building and contents coverage. It is on it's a data set from Wisconsin. It will be just I think 5 or 6 years, right? So here we have we leave 1 year for validation, the other years for training. This is not exactly a binary, right? Because this is the number of claims from a policy. So as I mentioned, most policies are clean. They do not file a claim. And one will be the next one that has the second highest number, right? And then goes towards, well, 8 all the way to 10 plus, but they don't really count more for each one. It's just putting into a category. So for such a multi-class classification, right, your first job is pick a threshold, right, so that you have a binary, right? Because our method is for binary, right? And you have many classes, right? So what I mean for the threshold is you pick a threshold H. Those on the left is a class. Those on the right is another class. Then you have a binary, right? Again, we tested the potential robust issue, right? We did 1, 2, 3, 4. It's just, after 4 is pretty much nothing, right? So I think that's a reasonable range. We didn't put 0, that's because for this particular case, 1 is quite significant, right? And another reason we don't do 0, that's because this is a government-sponsored program. That means you shouldn't just kick out those who have some risk, right? As long as it is not too risky, you should take, because that is for the general welfare. You are not a private company that is sponsored by Wisconsin. Of course, we did for all H. So here I only have space for 1. The good thing is, the sign of your estimation says something. By the way, those are your X. So they are 1, 2, 3, 4. You need to minus by 1 because one of the those type, I think I didn't put all of them. So they are not 5, they are only 4, right? Because the remaining one will be this miscellaneous, right? Everything else will be there. So it's a 7-dimensional X. Intercept is your alpha. So each value corresponds to a potential beta, right? So the value of beta actually says something, and most of them is somehow the same sign, right? Except here it's slightly different, right? Like I said, here our prediction is if your score is big, you should predict the 1, and the 1 is bad, right? 1 is a positive, right? Which means it has a non-standard risk. So you can see that city is positive, right? County is positive, but you see, town somehow is negative, right? Which means if you live in a small town, that's safer. So that's what the model says, right? And also we have some numerical or continuous X, like coverage, right? Meaning if you want higher coverage, you are more riskier, okay? But if you have higher deductible, you are less riskier. So that's the beauty of a linear classifier model. It's inseparable, right? You can tell whether this is a good or bad factor in pricing, right? Machine learning usually couldn't tell that much, right? And it is intuitive, right? Somehow what we imagine, right? Indeed, I have a friend who moved to Toronto from Alberta. He is still driving using Alberta license, Alberta plate, for the reason right? Because Toronto, you need to pay more for auto insurance. Back in Alberta, people are much nicer, so at least in driving. So that's what it says. So here we do again, we only consider exponential now. For the simulation, we did both exponential and logistic, but here we only do exponential, okay? And the message is quite clear. Again, your y-axis is false positive, or well, here we only do false positive. That's because we only want to consider the high sensitivity region. That's because this is a publicly sponsored insurance, which means you shouldn't just kick out those people who, well, somehow with relatively high score function, right? You should accept as many as possible, unless that particular policy is deemed too risky or uninsurable. So that's the purpose of this type of, this is because of the data set, right? So that's another reason why this is helpful, is when you have a different data set, when you have a different company, you can tune your perspective. So here, what we see is that I picked out this H to be much bigger. That is another thing we didn't explore, but I think it could make sense is when you have 3, right? This side, the left-hand side is total majority, right? This is a very, very imbalanced data, okay? Likewise for 4. So for very, very imbalanced data, we know logistics is not doing it. So that's why there are many, many people proposing alternative models. You see, the logistics, they are not doing well, especially you see here, right? Especially for 4. The higher the H, the more imbalanced the data becomes, right? So you can see that when data becomes more and more imbalanced, logistics is performing worse and worse. However, the exponential model is still doing relatively okay, or actually much, much better than logistic for here. You see, the gap is quite enormous, right? So the improvement can be substantial if you have a very imbalanced data. And nevertheless, the message is that exponential can always outperform. Right? For this specific region, the red line, the one with lambda being 0.9, is superior to the logistic, right? Because for this graph, the lower the better, right? So this even has no interception, right? It is strictly lower than the dash logistic model, right? And here as well. So the message, I think, is very clear. That is such a general approach with specific exponential family can do well in prediction. This is the AUC. Like I said, I already presented, right? For as long as you choose relatively large lambda, you can do much, much better than the logistic model. And those are the real data sets. I think there's no need to do the conclusion. I did that at the beginning, right? Here is some quick references. This is online at ResearchGate. You can also find it from my website if you are interested in this paper. And some of the papers I mentioned along here is an incomplete list. You can find all of them from the paper. Okay. I think that's the last slide. That's all here. So if you have any questions, feel free to ask.
Yeah. Thank you, Ben. Are there any questions? Okay, so maybe can I ask a question?
Yeah.
So is there a criteria for selecting the weighting function? So here you select the
Yeah.
to family because maybe reasons.
Yeah, that's a very tough question. Because the truth is we don't know that much. That's because it's too general. The family for the weighting function is really, really big. I'm not sure whether there will be better ones possible, right? Because here, this is what we consider, right? It is very, very simple. We also did this something slightly more complicated. It's actually similar to the exponential. So that's why for the empirical research, we only considered exponential, but for simulation, we considered both. I didn't show you in this talk. But to your question, we don't know. It can be, like I said, it shouldn't just stop here because this is such a general model, right? Any choice of W is a particular model. It's limitless. It's really up to you to think of a nice W. Here we put some analytical conditions on it so that when we do calculation, we know that we are not dealing with any issue in optimization, right? Because the second order condition, right, it's strictly greater than 0. So your minimization is going to get you the true value. But you can think of something different. That would be the paper.
But for the two families you mentioned, without pretty consistent.
Yeah. I didn't put the graph here, but we did this part. We did for the simulation, we did example 1 and example 2. I only showed you example 1. Okay? And they are close. And the exponential one is slightly better. Because what we have in mind is actually this. For many people, right? You don't need to really think of what W is, right? You should really think of the shape of your U, right? What kind of U you want, and you can go backwards because it's just integral, right? If you know the big U, you can go backwards to find the potential W because this is just the integral, right? So if you have a general idea of what kind of U0, U1 you should have, you can go backwards. Right? It's a calculus question. I'm sure that's solvable.
I have a sort of clarifying question. First of all, sorry if I ask something that you already covered, because I usually have my laptop, otherwise I don't see anything. So I just listen to you. But just to summarize, what you say, going back to your example of your admissions, right? Because as far as I see, what you try to do is to augment this classical model to be able to not just predict, because what usually you have is the classical problem, you have X, Y, right? You want to compute those alpha, beta, to predict how to classify the new X, right? How to find a new one, right? So in your case, you want to say, okay, I don't want to just predict, I want to predict under certain additional assumptions. So something happens to my macroeconomic conditions. For example, I have less students, I will allow more admissions, and therefore I'll have more, say, Y's in a certain category, correct?
Yes.
Okay. So now the question, if I understand correctly, then the question is this. You do this decision, you make this decision by, I guess, modifying your first and second statistical error, correct? But it's not really clear. I'm going to do a very free here. Sorry. I'm just thinking, okay, let's say I want to modify statistical error number 1, right? But how exactly, what it really means for which factors X I really prioritize when I admit or do not admit new students in your example. See what I mean?
Yeah.
So I would actually prefer to have a direct mechanism to say, okay, I want to now admit students with lower, say, GPA, right? Or with certain socioeconomic background. This way, I actually prioritize certain factors over others, right?
Yeah.
And I still increase my Y category. See what I mean? It's not really So this is my sort of point.
Yeah, so very nice question. So what we continue that example is what we present is that in good years, when we predict the zero, I want the GPA that's 3.8 is a zero. Okay? Zero means good. Okay? That's what I prefer to do. I think that is the most important thing when I do the prediction. Now, in bad years, I consider the other side. What I do is I only reject those with GPA, let's say less than 3. Okay, everything else I take. You see the point? Right? So because when I have a good business, I will only take those higher than 3.8. In bad years, I only reject those less than 3.0. You see the change of business objective, right?
Yeah.
Right. Yeah, but I see your point is how you can do that on X as well.
Yes, so because what you do is it's connected to the distorted probabilities, right?
Yeah.
So you can distort probabilities with some weight functions as well, and you can actually do those weight functions like what you do. It's like a function r plus n to something, right?
Yeah.
Then you sort of distort different. So I was thinking along this way, but because I don't really see the formulas, it's very hard trying to really check.
Yeah, that is deep. Yeah, indeed. I see your point. And to those who don't follow, it's well, when you distort, right? You can have everything aggregated first and then distort. That's what we do here. And what Alice does, you can distort first and then you
aggregate. Right. And it's connected to what Dong Chen asked about the choice of the weight function. Because this way you can maybe argue for certain choices.
Yeah. But that's a very good question. Yeah, thanks for that. Indeed.
Maybe our virtual attendees have some questions. If any of you have questions, please unmute yourself.
Doesn't look like probably they are not incentivized because they don't have access to cookies.
Okay, so I guess if no questions from the audience online, I'm gonna stop here. We're gonna thank Dr. So for this wonderful talk.